Hello students, sorry for this long gap. Actually, I've been facing some problems with my technical setup at home, and only after I could solve them, at least for the time being, I could prepare this lecture and meet you over this video lecture once again. Today, the topic we are going to discuss is coherence. Coherence is very important. We have been talking about coherence since long, actually, from the very initial classes on the topic of interference. But as I always do, before I begin the topic of coherence, let us first have a brief recapitulation of the last lecture. In the last lecture, interference by division of amplitude has been discussed. Interference by division of amplitude due to a thin film of phases having a small angle alpha have been discussed. You will remember that a very rudimentary thing was taken initially. It was a thin film, and generally we expect the thin film to have parallel faces, but no, this thin film did not have parallel faces. Though a very small angle, it had a very small angle between the faces, and the angle was denoted by alpha. The path difference of the two reflected waves were calculated, and yes, for two consecutive reflected waves, the path difference delta was found to be twice mu t cos r minus alpha. And for two consecutive transmitted waves, the path difference delta was found to be twice mu t cos r minus 2 alpha. When alpha, as I told you, is the angle between the faces of the film, r is the angle of refraction, mu is the refractive index of the material of the film, and t is thickness of the film at the location of interest. As I have been discussing since we took up the topic of Lloyd's mirror, remember, the light wave reflected while passing from a rarer to a dense medium had an extra path lambda by 2 or an extra phase of pi. Always remember this. A technical discussion on this has been done in the very previous lecture, so I'm not going to repeat this, just remember this. Then in the last lecture we discussed the wedge-shaped film and Newton's rings arrangements. For the wedge-shaped film, extended source was used, and fringe width beta was found to be lambda by twice mu alpha. When mu was the refractive index of the wedge, alpha was the angle between the angle of the wedge actually. So when alpha is large, from this expression it is evident that the fringes will be very fine. When alpha is small, it will be thick. If wavelength is very large, likewise you can guess what will be the nature of the fringes. In Newton's ring arrangement, extended source was used. A thin air film was formed using a plano-convex lens and a plain glass plate. The wavelength of unknown source could be determined using a Newton's ring arrangement, and the formula is lambda is equal to mu into dm plus p square minus dm square by 4 mu capital R, when dm plus p is actually the diameter of the m plus p at dark ring, dm is the diameter of the mth dark ring, and capital R is the radius of curvature of the ring, which is generally quite large. The ring width was given by the formula beta is equal to lambda R by mu dm. Okay. So from this formula it is evident that as we go farther away from the central spot to rings having larger diameters, their widths will be less. And we also did a peculiar problem of raising the lens in Newton's ring arrangement. It was found that raising of the lens in Newton's ring would cause collapsing of rings to the central spot. So that is as far as our brief recapitulation of the last lecture goes. Now we will begin our fresh topic of coherence. So before we approach coherence, since coherence, this concept came while we started discussing the conditions for sustained interference pattern, let's have one small recap of the conditions for sustained interference pattern. We have since the very beginning of this course discussing, we have been since the very beginning of this course discussing about and referring to the conditions of sustained interference pattern. It is imperative that we take a look back at the conditions again. As I just told you, the conditions for sustained interference pattern are the two sources light from which interfere must be monochromatic. Okay, that means they must emit waves of a particular wavelength or a particular frequency, nothing around it. Okay, only a particular value. And also they must have the same frequency. The two sources must have the same frequency. And what was the okay? So actually, if we look at real world, there is no monochromatic sources. Why? Because even a typical lab source or any source you can think about, it emits a small band of frequencies. Laboratory sources actually have this bandwidth slightly greater than lasers. However, both are emitting bandwidth of frequencies of light, which are around a particular average value, and it is our way of calling such bandwidth as monochromatic and denoting the frequency or wavelength of that monochromatic wave to be the average value of frequency and wavelength. The second condition for sustained interference pattern was the two sources of light must be coherent. I don't know how many times I have been telling you about this. Now, coherence is a very interesting condition. Coherence is the topic to be primarily discussed, as I told you in this lecture, and this is related to the first condition. That is, though these two conditions are approached differently, but they root from the same cause. Now, as I told you, that no source is actually monochromatic, they are quasi-monochromatic. Quasi-monochromaticity means that light wave does not consist of a single frequency sinusoidal wave as imagined while dealing with phenomena of interference mathematically. We always take the ideal condition when we treat something mathematically, at least initially. So quasi-monochromaticity means that it is not one single frequency that a source is emitting and a nice sinusoidal wave a source is emitting. A typical laboratory monochromatic source produces light by electronic transitions, and the transitions have durations of the order of 10 to the power minus 9 to 10 to the power minus 10 seconds. That is the most important point. That is the reason why no source is monochromatic. I'll come to that. Now, if for a finite or minute duration a transition is taking place and that transition causes emission of wave, then you cannot expect a continuous infinitely extended wave to come out of such minute duration transitions. So obviously it will be a wave pulse that is emitted. Okay, now how is the shape of the wave pulse? That depends, but definitely it's a wave pulse. It does not have an infinite extension, it is only extended up to a finite length. That is the relevance of a wave pulse. Do not consider from a quasi-monochromatic source that light wave will come out as a continuous beautiful sinusoidal wave. Such a wave pulse can best be imagined by considering a superposition of waves with a narrow range of frequencies about a mean frequency. This is Fourier This is a Fourier series. You just approach by considering how to construct such wave train or wave pulse. You superpose waves of frequencies lying in a certain range of frequencies. You can construct different wave pulses. Okay, that's just for you to understand how to think about a wave pulse. Okay, conditions for sustained interference pattern are being continued, and we are talking about what is quasi-monochromaticity, and we have understood, we have known. I have been telling you earlier also that the electronic transitions that cause emission of light from any source, or for that matter typical sources like that we find in our laboratories, say a sodium source, a helium source, these transitions have a duration of 10 to the power minus 9 seconds to 10 to the power minus 10 seconds. So this is the root cause, and it is because that such minute duration transitions takes place, we cannot consider that a light wave is coming out of it as a continuous sinusoidal wave. Rather, it comes out as a wave pulse. So the electronic transition duration of 10 to the minus 9 second to 10 to the minus 10 second is also the reason why two ordinary quasi-monochromatic sources are generally not coherent. Why? Let's see. Two sources are said to be coherent when there is a constant phase relation between the waves emitted by them. This is the most important, constant phase relation. If there is a phase difference between two waves, then that phase difference remains. It does not change with time. That is what we need for two sources to be coherent. Electronic transition duration have been stated already, and within a source many such transitions take place randomly. Okay, you cannot say when a particular electron will transit. Though the same condition of energy is given, it can one electron can absorb energy at one instant, another electron will absorb energy at another instant, and that too when it will undergo transition, nobody can say. So such transitions take place randomly. Now look at this. This is the wave pulse I have been talking about. See, now the figure A is basically giving you the type of wave you expect from a source due to a transition which is taking place for an infinite time. Okay, so that's why this wave is a continuous sinusoidal wave, and its time period, as has been shown here, sorry, is 2 pi by omega 0. Okay, when omega 0 is the frequency of the source, and as I've told you that such sources which will be giving out continuous sinusoidal waves are perfectly monochromatic. They are not quasi-monochromatic. I'll come to this point later also. Why? Because I have already told you continuous waves are simple one frequency waves, but that is not the case for wave pulses. You look at this one, the figure B. Here you see there is a kink here. Here is a kink, and here is another kink. So this wave is not continuous, and the wave A to B is actually a continuous wave. In between there is a constant phase relation. Okay, now after you have taken a look, let's discuss this point in a more detailed way. Yeah, figure A shows a continuous sine wave that is often approximated as a light wave from a source. Yes, we always mathematically consider there is a beautiful sine wave coming out. T is equal to 2 pi by omega is equal to 1 by nu is the time period of such a drastically approximated light wave. It is a drastically approximated light wave. No light wave is actually like that. Figure B, sorry, figure B represents a somewhat realistic light wave. The kinks at A and B speak of minute electronic transitions, transition durations denoted by tau c. See, at point A transition had taken place. A transition, a light wave that was due to some previous transition ends at point A and another one begins at point B. Likewise, there is one transition ending. So the phase is totally changing randomly. You can check. The phase is changing randomly. Here, this kink is there and this kink is there. So this time duration is called tau c. Why? Let's see. The kinks at A and B speak of minute electronic transition durations 10 to the power minus 9 seconds, 10 to the power minus 10 seconds, denoted by tau c. Okay, tau c is called the coherence time. Any 2 points lying in the range AB, that means any 2 points lying between A and B. And what is the distance between A and B? It is c into tau c. C being the velocity of light, and tau c, as I told you, is the coherence time. So this is the distance will be coherent to each other. Why? Because between A to B there is no random change of phase. The phase is continuously, beautifully changing, it is continuously changing. So that's why any 2 points lying in the range AB will have a constant phase relation to each other. That's the most important point. Okay, so let's proceed. Tau c, as I just told you, is called the coherence time, and LC, that is the distance corresponding to tau c, which is the product of the velocity of light c and the coherence time, is called coherence length. Do not mix up coherence time with temporal coherence, and do not mix up coherence length with temporal coherence. There is a relation, but they're not the same thing. In a realistic light wave, if 2 points are at the most LC, that is c into tau c, distance apart, there will be a constant phase relation between them, or they are correlated. Okay, just as I had shown you in the figure, between A and B there is a constant phase relation. So any point between A and B, any 2 points, take any 2 points between A and B, that means in the range LC, they will have a constant phase relation, or their phase will be correlated. Some examples of coherence time and coherence length. Now we have been having just a discussion. Now let's have a practical approach. For the neon line lambda 6328 angstroms, we find that tau c is 10 to the power minus 10 seconds. Okay, if tau c is 10 to the power minus 10 seconds, 10 to the power minus 10 seconds, LC can be found out by just multiplying 10 to the power minus 10 seconds by 3 into 10 to the power 8 meters per second. That is, so LC is found to be 3 centimeters. So what do we expect for neon? Any 2 points which are lying between 3 centimeters from in a wave that is emitted by neon 6328 angstrom, these will be related phase-wise, or they have a correlated phase. Okay, let us take another example. Cadmium red line, a very popular line, to tell you the truth. Lambda for cadmium red is 6438 angstrom, tau c is 10 to the minus 9 seconds. So LC in case of cadmium is quite large, it's 30 centimeters. So any 2 points which are between 30 centimeters in a wave can be considered to be coherent, or they will have a constant phase relation between them. The real light wave produced by electronic transitions of minute lifetimes can be more complicated than truncated sine waves as shown above. Here I have nicely shown you the truncated sine waves are there, but the real wave, if you consider them, they are not as simple as that. Okay, they are not as simple as this truncated sine wave. I have just shown you this truncated sine wave to make you understand the thing quickly. So how is the real light wave? Now it requires more involved mathematical tools like the Fourier series expansion to thoroughly conclude about tau c and subsequently LC. Okay, since the real light wave is not a simple truncated sine wave as has been shown in this figure. Likewise, to conclude about tau c and LC, it is very difficult. It cannot be done very simply. However, despite of that, such detailed analysis does not lead to conclusions much different than what has been arrived at here using a simpler model of reality. For a more detailed discussion on this, you can see Optics 4th edition by Hecht and Ganeshan. It has a very detailed discussion. Which chapter you have to read, you can just contact me over phone or email. I'll let you know. Okay. Just remember, though this is a very simplest representation of a real wave, the real wave is actually not so simple, not even the truncated sine wave, but whatever it is, it can be understood by doing Fourier series, this and that, but whatever it is, the conclusions is the same. That means continuity of phase is important, and based on continuity of phase, we can define the coherence time, the coherence length. So let's proceed. Now, let us understand what is temporal coherence and how it is related with coherence time. What is coherence time? It is the time of transition, basically. At any point in a light wave from a source, the field oscillates with its phase changing continuously for a while. Why for a while? Because the transitions themselves are momentary. Okay, 10 to the power minus 9 or 10 to the power minus 10 seconds for a typical source found in the laboratory. Now, so its phase changing continuously for a while, then it changes phase randomly. When it is going to change phase, nobody knows. The coherence time only gives you an average idea, okay, not the exact value of time after which the phase will change. So that is why it will change its phase randomly, and that too to a random value. What will be the new phase? Nobody knows anything. Okay, that's why random value. Temporal coherence is a measure of the interval over which the phase of the light wave changes continuously. Is a measure, temporal coherence. So temporal coherence is a measure of the interval over which the phase of the light wave changes continuously. So between two such random transitions, temporal coherence gives you the measure of the interval. Tau c, as we know, is an average duration for which the light wave oscillates in a predictable way. Okay, so tau c is not the exact value. It is not temporal coherence. Tau c is just an average value. It can be slightly more, it can be slightly less than tau c. That is the duration for which the wave remains phase-wise continuous. Okay. Tau c, as we know, is an average duration for which the light wave oscillates in a predictable way. That is, on an average for tau c time, the phase changes continuously. Longer the tau c for a particular source, greater its temporal coherence. Obviously, now particularly let us take the example of helium neon laser. For helium neon laser, tau c is 50 to 10 to the power minus 9 seconds. That's why lasers are very coherent. Means much more coherent than the typical laboratory sources. And you see the coherence length is 15 meters. So in a wave coming out from helium neon laser, 2 points, as long as they have a distance quite less than 15 meters, they will be coherent. You see, they are much coherent, they have much more coherence, temporal coherence than any typical source found in the laboratory. Spatial equivalent corresponding to tau c, as already defined, is LC. Greater the temporal coherence, more monochromatic the source will be. Why is this? Now, temporal coherence means the duration for which the phase changes continuously. Okay. So if it's a long time, then how will I approach it frequency wise? Now, whenever it's a truncated wave, I've told you that can be constructed by superposing several frequencies, not one frequency. Okay. Now, if you have a very long duration sinusoidal wave, it takes lesser frequencies. The bandwidth of the superposing frequencies reduce. This is a qualitative way of understanding it. A more rigorous approach would be to take refuge to Fourier series. So that is why greater the temporal coherence, more monochromatic the source will be. But nevertheless, it will always be pseudo-monochromatic, never perfectly monochromatic. And finally, temporal coherence and coherence time, tau c, are related, but they are not the same thing. As I've told you, temporal coherence is a measure of the interval over which the phase of the light wave changes continuously. Okay, it keeps changing around a average value, and that average value is the coherence time, tau c. Okay, now let's see it graphically. See, here we have a point source at this point, and from this beautiful circular waves are coming out. We are considering some points p1 prime, p2 prime, p3 prime, p4 prime, and some laterally spaced points p1, p2, and p3 here. Okay, if the source was ideally monochromatic, this is an ideally monochromatic source. Why? Because see, all nice waves are coming out and all of them are equispaced. That's why if the source was ideally monochromatic, the wave would be a perfect sine wave, as is shown in the diagram, with tau c and LC unlimited. So for a perfectly sine wave, no need of bothering about temporal coherence. And so tau c will be infinite, so will LC be unlimited. In the adjacent figure, the wave which arises from a point source is monochromatic and has complete temporal coherence. What happens at p1 prime consequently will a moment later happen at p2 prime and later at p3 prime, totally predictably, as phase changes continuously in a predictable way in between. There is no rapid or random change of phase because it's a monochromatic source, perfectly or ideally monochromatic source. So it has a electronic transition time very long, infinite. So tau c is unlimited. So LC is unlimited. So we don't need to worry about coherence here. From the phase at p4 prime, the phase at p1 prime can be accurately determined. Of course, they can be determined because they are phase-wise related. Phase is changing only continuously between p1 prime and p4 prime. Every point on the wave is correlated in phase, the tau c being unlimited. The behavior of the waves at points p1, p2, p3 is completely correlated as they have the same phase with no disruption in between. P1, P2, P3 are the angularly displaced points, okay, from the point source. So there also phase is same. Nice circular waves are coming out, so no problem. Keep an eye on these 3 points in the next figure here. Now, what is temporal coherence in reality? That was the ideal case. Here we were discussing the ideal case, okay? Now, in reality, this is the picture of reality. What do you see here? See, waves are coming out, but their wavelengths are different. Short pulses are coming out for this duration. See, it has a certain wavelength, certain frequency, but for this duration, it has a different wavelength and different for this duration. It has a different wavelength and different frequency. Okay, why? Because the source is having electronic transitions which are finite in time, and that's why it is emitting truncated waves. Okay, that's why it is not monochromatic either, because truncated waves are constructed by superposing several frequencies. So let's proceed. For a real source, light wave will not propagate as a perfect sine wave, as has been shown in the figure. Tau c and LC will have finite values. The phase at all the points of the wave will not be correlated anymore. Of course, here you see P2, P3 prime are close enough, they are correlated, but P4 prime is far away. See, their wavelength is different there. Likewise, if there is a point here, that will also not be correlated. It will have a random change of phase in between. The phase at all points, all the points of the wave will not be correlated anymore. As shown in the figure, far apart points like P1 prime and P4 prime will not have any correlation. The points close by like P2 prime and P3 prime are still phase-wise correlated. This is a case of partial temporal coherence, a measure of which is LC and tau c. Now we have to worry about LC or tau c. Why? Because it's partially temporally coherent, not infinitely, not perfectly, not ideally. Over a length LC on an average along the wave, the phase varies continuously and is predictable. Once again, the points P1, P2, and P3 are on a wavefront that originates from the same point source. But here, once again, like the previous case, the point source is here. We are not using any extended source. That is why P1, P2, P3 are still correlated. They are not affected. Although this source is a real source, it is quasi-monochromatic, it has limited temporal coherence, it has a coherence time that is finite, but still the points which are angularly displaced from the source are phase-wise correlated. Why? Because it's a point source. This is the thing we will be losing when we use an extended source. We are going to see. P1, P2, P3 are then phase-wise completely correlated here as well. This phase-wise correlation of P1, P2, and P3 is irrespective of the temporal coherence, because earlier we had ideal temporal coherence. Here we have partial temporal coherence, but despite of the fact that the temporal coherence has changed, P1, P2, P3 are still correlated. So it is irrespective of the temporal coherence as long as a point source is used. That's most important, as long as a point source is used. Now we are coming into spatial coherence. Okay, let's see. This was the case of point source of limited temporal coherence. For a point source, there may be a random phase change along the wave due to partial temporal coherence. But at a particular distance from the source, for all the points like P2, P3 spread angularly, the phase remains correlated. This being an example of spatial coherence. Okay, this is called spatial coherence. That despite of the fact that it has temporal coherence, limited temporal coherence, the source, since the source is a point source, angularly spread points will not have any problem having a constant phase relation or a continuous phase relation between them. This phenomena is called existence of spatial coherence, but this is destroyed when an extended source is used. Here, it's a very complicated diagram. You can just see. The point you should focus is, see, there are on the left of this square, you can imagine there are more than one point sources, okay, and each one of them is emitting a circular wave. So in the rest of the space, the intensity depends on how these different circular waves superpose on each other and what's the resultant intensity they are giving. Okay, now we are using a broad source. What is a broad source? Point source along a straight line can be considered to be a broad source. Each point source emit wave trains phase-wise independent of each other. When one point source of the broad source will emit and when another will emit, nobody knows. Why? Because there is limited temporal coherence. And there is a coherence time where that is finite here, not infinite. So the distance P1 prime, P3 prime, when it is very, very less than LC, P1 prime, P2 prime, and P3 prime will be correlated phase-wise. Okay, there is no problem of having temporal coherence for P1 prime, P2 prime, and P3 prime, because their distance is not very large, it is very, very less than LC. But resultant wavefront will have equidistant jagged wavefronts, not circular for duration. Why jagged? Because I said if it was a point source, beautiful circular wavefronts would come out. But if there are many point sources, the beautiful circular waves from all these point sources will superpose on each other, and we will give, who knows, a zigzag or jagged pattern of wavefront. Okay, and remember, this jagged pattern is going to change with time also. So resultant wavefront will have equidistant jagged wavefronts, not circular, for duration less than, very, very less than tau c. But these, whatever jagged they will be equidistant. There will be an equal distance between them, or their frequency and wavelength will remain the same, despite of the fact they are not circular waves, they are jagged waves. The frequency and wavelength remains same. Only after tau c, this is going to change. But as long as the points are remaining inside this LC, in this range LC, they will have a constant phase relation. Temporal coherence will be there. But for t greater than tau c, two or more waveframes all having jagged wavefronts, but each with different jaggedness and different spacing. What does it mean? When t is greater than tau c, two or more waveframes will be there. Their jaggedness will be different. How zigzag they are, that is going to change. And their spacing or the frequencies are also going to change. Just like here. Here it was a point source that was circular. Waves were emitted, but as their spacings varied due to temporal coherence, as t is greater than tau c, their spacing varied. Here also the jaggedness will vary and the spacing will vary. Why the jaggedness will vary? Can you guess? Because different points are transiting at different times randomly. Nobody knows. So if a particular point has a transition, its wave pattern will change. That will change the shape of the resultant wave pattern in the space. So till now, a qualitative discussion on spatial and temporal coherence has been done. So did you understand why spatial coherence is lacking here? Here spatial coherence is lacking because the jaggedness is changing. Okay, because the wave fronts are not circular, they are having a random shape. And not only that, if a duration is crossed, that is of the order of tau c or equal to tau c, then even the random shape will change. Okay, that is why along, if the angular spread, the phase won't be correlated, and p2, p1 and p2 will never have a phase wise correlation. So this is lacking of spatial coherence. Till now, qualitative discussion of spatial and temporal coherence has been done. Before we proceed for a more application-oriented discussion, let's touch up the salient points. A typical point like light source generates light due to electronic transitions of duration 10 to the power minus 9 to 10 to the power minus 10 seconds. Wave trends rather than infinitely extended sine waves are emitted, hence the source is quasi-monochromatic. Points along such a wave having distance very, very less than LC, when LC is equal to C into tau C, are phase-wise correlated. Tau C and LC are measures of temporal coherence. Points equidistant from the point source are always phase-wise correlated. That is, when points are equidistant from the point source, that is, we are only considering angularly spread points, not distance-wise spread points, they will always be correlated as long as we are using a point source. For point source, spatial coherence is infinite. When broad source is used, because broad source is a series of point sources emitting waveframes randomly, resultant waveframe will have a series of similar jagged wavefronts for not for infinite time, only for times that is very, very less than tau c. So inside this regime of similarly jagged but similarly jagged wavefronts, temporal coherence will be there. But what is lost? Spatial coherence will be lost. For distances very, very greater, the width of the extended source, that means if I am considering very long distances from this broad source, spatial coherence is once again restored. This is a beautiful thing. There is a beautiful video in YouTube. I can, in fact, not if not in YouTube, I can send you the video. It is an example when some ducks are plunging into a pond. When they plunge into the pond for a certain distance, the wavefronts emitted are jagged. But after a while, that is after quite a long distance from the point where these ducks jumped into the pond randomly, the waves are having circular shapes. As they become circular, then obviously all points angularly spaced will be phase-wise correlated. Okay, please approach me. I'll let you know where you to find this video. It's a very nice video. Everyone should see this. So that is it. Now let's go into the quantitative discussion of coherence. Young's double slit arrangement interference pattern only around the zero order fringe. Okay. In Young's double slit arrangement, when we really do it, though theoretically there is no problem, we should have a very extended interference pattern, but in real life we always see that the interference pattern is only limited at a certain region of space around the central spot or the central fringe. So this is the diagram. S is the main source, S1, S2 the two secondary sources done by making two slits on a barrier, and OP lies on the screen. O is the location of the central fringe, P is the location of any arbitrary fringe. At an instant t, the intensity at P is due to superposition of waves emerging from S1 at time t minus R1c and S2 at time t minus R2c. What is R1? R1 is S1p, R1 is S1p, and R2 is S2p. Why it is t minus R1c? Because the wave approached from the source. Okay, if I'm considering at the instant t, the wave had started from S1 at t minus R1c and from S2 at t minus R2c. Ideas of temporal coherence and tau c tell us that for R2 by c minus R1 by c, this time, okay, if this time is very, very less than tau c, then temporal coherence will be present and interference pattern will be obtained. Okay, as long as temporal coherence is present, no problem, isn't it? We can consider all our calculations to be correct because phase is changing continuously beautifully. But if there is a random change of phase, every calculation crushes down. So as long as R2 by C and minus R1 by C, this quantity, time quantity, is very, very less than the coherence time, temporal coherence will be established and interference pattern will be obtained. But if we go far off, if we take P quite wide off, what happens? When R2 by C minus R1C becomes comparable, temporal coherence condition will not hold and no interference pattern is obtained. This explains why in Young's double slit experiment, the interference pattern is only visible at a small area, because if OP is increasing, okay, as OP increases, this quantity R2 by C minus R1 by C is going to increase. Why? Because R2 and R1 is going to increase. Okay, so there may be a reason, there may be a location when it is going to become comparable with the coherence time, the quantity R2 by C minus R1 by C, and we will have a sudden change of phase and all our calculations will go down and the interference pattern will vanish. Why it will vanish? Then after a while again it will change randomly. So there will be a flicker. So we will never be able to see any sustained interference pattern. Wave trains rather than infinitely extended sine waves are emitted. Hence the source is quasi-monochromatic. The key idea. The path difference of the two superposing waves should only change with space and not time. Okay, if it is going to change with time, gone. We are not going to get the sustained interference pattern. So keep close to the point O, you are going to get a sustained interference pattern. As you go far off, things are going to change randomly and you're going to lose the interference pattern. Now we are going to have a discussion on coherence in the context of Michelson's interferometer. Don't be worried because you have not studied Michelson's interferometer in my class, but it's a very simple thing. I'll show you what it is, and the idea that is going to be involved in discussing coherence in this context is very simple. You don't need to worry. So this is a Michelson's interferometer. Look at it. See, this is the source. There is a slit. Light wave is coming. Okay. First P1. P1 is what? A half reflecting plate. 50% of the light that is incident on P1 is reflected and 50% is transmitted. So after P1 there is another plate which is called the compensating plate, which has the same thickness as P1. Then there are two mirrors perpendicular to each other, M2, M1. The angle may change, but generally for our case let us consider them to be perpendicular, M1 and M2. So let's take this first ray that is approaching from S. At point B1 it is getting reflected. It is approaching M2, getting reflected there, again getting refracted through P1 and entering the telescope. From B1 another ray is transmitted to this compensating plate P2 at B2. Okay, it gets transmitted through this plate because it's not a half reflecting plate. It plainly gets transmitted, reaches M1. From M1 it is reflected back to P2, passes through it nicely because it's a simple glass plate which has the same thickness as P1. Then it is incident at P1 and gets reflected through the telescope to the eye. At P1, at C1, sorry, at point C1, it is also getting transmitted, but we are only considering the reflected wave. Okay. So here two rays are approaching and superposing at the telescope, and each one of them are traversing the same distance as long as the distance of M1 and M2 from the mirror, from the half reflecting plate P1 is the same. This is the idea you need to understand. Now if I move M2 a little away, what will happen? The two rays will not have the same path traveling. One of them will travel a longer path, and there will be a path difference, as a result of which we might have different intensity. So this is it. A Michelson's interferometer consists of S, a monochromatic lab source, that is a quasi-monochromatic source to be precise, P1, a half reflecting mirror, P2, a compensating plate, M1 and M2 mirrors perpendicular to each other. Tracking the light wave from S, we see, that's what I've been telling you when we zoomed into the diagram. B1 is light, B1 is the point. Light from S gets partially reflected by P1 here, gets reflected by M2 again, and enters the telescope T. The rest gets refracted to B2 on P2, gets refracted again to M1, gets reflected back to C1 through C2. This is what I've been telling you when we zoomed into the diagram, where it is reflected again to T. P2 is the point which has the same width as P1. Sorry, P2 is the glass plate, or it is a glass plate, it's not a mirror. P2 is the glass plate which has the same width as P1 and is taken to compensate for the extra optical path traveled while the wave moves from M2 to T, so that the thickness of the P1 does not come into the calculation. That's why we are placing P2. The idea is to keep M1 and M2 equidistant from P1 so that the two waves interfere constructively at the eyepiece of the telescope. They will be equidistant, and hence the path traversed by the two rays will be same, so there will be zero phase difference. If M2 is shifted by D, dark and bright circular rings appear, provided M1 and M2 are perpendicular to each other. If they have an angle, we will get fringes of different shapes. We are not going into that. Just understand that if they are perpendicular, we'll get dark and bright circular rings. Shifting M2 by D, as I was telling you, if now the distance of one of the mirrors is shifted here, we have actually shifted M2 by D. When we shift that, what happens? Obviously, the ray that is being reflected by M2 traverses a greater path. Hence, when they coincide, when they superpose at the telescope, one of them will have a greater path and there will be a path difference, and depending on the value of the path difference and whether it's an integral multiple of the wavelength or an integral multiple of half the wavelength, we will have bright or dark fringes. Mind it, they are both getting reflected while traversing from a rarer to denser medium, so nobody is going to have an extra phase of pi or an extra path length of lambda by 2. Indefinite increase of d, however, leads to disappearance of interference pattern. Okay, you cannot go on increasing d. Why? The same thing. It is going to have a length that is greater, that it becomes comparable to coherence length. Let's see. The reason being, once again, temporal coherence. Yes, temporal coherence, hence coherence time, hence coherence length. The waves reflected should superpose at t in such a way that the extra time taken by the longer traveling wave is, that is, what is the extra time? The distance is 2d divided by c, so you get the extra time traveled by the longer traveling wave. It is 2d by c due to extra path. 2d traversed is 2d by c, very less than tau c. That means as long as the extra time taken by the longer traveling wave is very less than the coherence time, we are going to get interference pattern. But if you go on increasing d indefinitely, what will happen? At one point, 2d by c will become comparable to the coherence time tau c, and temporal coherence will be lost and the interference pattern will disappear. Michelson interferometer gives interference pattern using two mirrors, here M1 and M2, and a half reflecting plate, here P1, using the division of amplitude principle. That you have already understood, I guess. Now, for a neon line, which has lambda, as I told you, 6 to 8 angstroms, the disappearance occurs when the path difference is about a few centimeters, giving tau c is equal to 2d by c is equal to 10 to the power minus 10 seconds. So we are doing a back calculation. We are seeing from when is this interference pattern disappearing, when are the rings disappearing. If they disappear, okay, this is the distance. Okay, from that we can guess what is tau c. So using this Michelson's interferometer, we can always guess the coherence time and hence the coherence length by watching at what distance the interference pattern is destroyed. Like for neon, which has a wavelength of 638, for that particular neon line, 638 angstrom wavelength, we see using this approach that taking tau c is equal to 2d by c, that the coherence time is 10 to the power I'm sorry, it will be 10 to the power minus 10 seconds. Please make corrections. It's going to be 10 to the power minus 10 seconds. Likewise, for cadmium red line, which is 6438, likewise calculation will show us it is 10 to the power minus 9 seconds. Please make the necessary corrections. So what we see is using a Michelson's interferometer and finding 2d, that means the distance after which the interference pattern is getting destroyed, it's vanishing. We can always guess the coherence time of the source. That's a very interesting experiment actually. Now coherence time we have talked about. Now let's talk about spectral. How coherence time is related with spectral line width. Interference may disappear when source is not monochromatic. Okay, why? Because if source is monochromatic, then it is coherence time is infinite. Remember all that discussion. So we can directly connect these two things. Interference may disappear when source is not monochromatic. It's quasi monochromatic, that is, there is limited temporal coherence. Interference may disappear. source having two wavelengths, lambda 1 and lambda 2. Now we are first using a source having two wavelengths, emitting two wavelengths, lambda 1 and lambda 2. Interference pattern disappear when Imax for lambda 1 coincide with Imean for lambda 2, or it may be vice versa. For that moment, let's take Imax for lambda 1 coincide with Imean of lambda 2. For disappearance, what do we need? We need 2D is equal to 2m lambda 1 by 2. Okay, we are discussing this in the context of Michelson's interferometer only. That is why the path difference is 2D. And there is always, so what uh, for I mean we will have an half integral multiple of lambda. So that is why 2D when it is equal to 2m lambda 1 by 2. Okay. I'm sorry. For lambda 1 we are getting the maximum intensity, hence it will be an integral multiple of lambda. So 2D must be equal to 2m lambda 1 by 2. And for lambda 2 it will be a half integral multiple of the wavelength, hence we have 2m plus 1 by 2 lambda 2. When delta is the path difference, it's equal to 2D. Okay. Now from this equation we can find that m is equal to 2d by lambda 1 is equal to 2d by lambda 2 minus half. Now equate these two and we get what? Yes. Or 2d by lambda 2 minus 2d by lambda 1 is equal to half. This implies that 2d is equal to lambda 1 into lambda 2 divided by twice the difference of lambda 1 and lambda 2. This is a very important formula. We are going to use this. When lambda 1 and lambda 2 are only having a difference of delta lambda, that means lambda 1 is equal to lambda 2 plus delta lambda, and lambda, that is the average of lambda 1 lambda 2, is denoted by the wavelength value lambda only. We have 2d is equal to lambda square by twice delta lambda. For difference we have taken delta lambda, and for the average we have taken the product of lambda 1 by lambda 2 as the average square, that is lambda square. If source has a range of wavelengths from lambda to lambda plus delta lambda. Now earlier we have been discussing about two wavelengths. Now there is not two wavelengths but infinite number of wavelengths may be at a certain range, lambda to lambda plus delta lambda. What happens then? For the Imax of lambda and the I mean of lambda plus delta lambda by 2, that is halfway through the range, or the other way around to coincide, we must have 2d is equal to lambda square by twice delta lambda by 2. We have just replaced by delta lambda. We have just replaced delta lambda in this formula by delta lambda by 2. Why? Because we are considering two wavelengths, one lambda and another one lambda plus delta lambda by 2. Okay, so that is then 2d becomes lambda square by delta lambda. For each lambda in the range lambda to lambda plus delta lambda, there is a corresponding lambda in the range lambda plus delta lambda by 2 to lambda plus delta lambda, for which the interference pattern will disappear. For the first half, if there is a wavelength, then for a second half, there will be a corresponding wavelength for which this will interference pattern will disappear, provided 2d is equal to lambda square by delta lambda. For 2d greater than equal to lambda square by delta lambda, then we can say that the contrast of the interference pattern will be too poor. It's going to be very poor. It's almost not visible. Why? Because even if we increase the half range, there will always be some wavelength which will cancel out. That is why even for greater values, we are going to lose contrast in the interference pattern. So for line width delta lambda greater than lambda square by 2d, the contrast of the interference pattern will be too poor. So how long are we going to, we said, we just were discussing earlier that all sources are quasi-monochromatic. Okay, so every source will have a bandwidth in wavelength. But can it have a large bandwidth? No. If it has a large bandwidth, we are going to lose the interference pattern. So what is the way out? Controlling D is the way out. Comparing LC with 2D, we have now just replace 2D by LC. So delta lambda is lambda square by LC. or delta lambda is equal to lambda square by c tau c, because L c is c into tau c. So delta nu is of the order of 1 by tau c, or approximately equal to 1 by tau c. Why? Because nu is equal to c by lambda. That tells us that delta nu will be c by lambda square into delta lambda. Okay. So we are now relating the monochromaticity, that is the bandwidth of frequency delta nu with the temporal coherence. This is also illustrating in a more rigorous way why monochromaticity and temporal coherence are correlated. Okay, now we are going to discuss spatial coherence. See, we are considering a finite dimension source. The experimental arrangement is simple. It is a Young's double slit arrangement with secondary sources S1, S2. Just two sources are being used for the time being, S and S prime at a distance L, and the two slits are at a distance small d. Okay. Point sources S and S prime, distance L apart, illuminate slits S1 and S2 when S1, S2 is equal to d. S prime, S2 intersects SO. S prime, S2. This line, S prime, S2 intersects SO prime. I hope you can see O prime at N at an angle alpha. Sn is equal to A1 and NO prime is equal to A2, and we have A1 plus A2 is equal to A is equal to SO prime. Okay. For Imax of S, that is for intensity maximum of S and intensity minimum of S prime. Now there are two sources, two primary sources are being used, so each of them will give an interference pattern. So it may happen that one of the maximum of one is, the intensity maximum of one is falling on the intensity minimum of the other. So for them to coincide, we must have S prime S2 minus S prime S1 is equal to lambda by 2. At least. It can be any integral multiple of lambda by 2, but at least it should be lambda by 2. Now S prime S2 is what? If you look at the diagram, S prime S2, excuse me, S prime S2 is A square plus D by 2 plus L whole square to the power half. Okay. And you just expand it binomially and neglect the higher order terms, which has d plus L by 2a, because d and L both are much smaller than a. Okay, that is the distance between the two secondary sources S1, S2 and the distance between the two primary sources S and S prime are both much smaller than a, so we can neglect the higher order terms. So S prime S2 becomes a plus 1 by 2a into d by 2 plus L whole square. Likewise, S prime S1 becomes a square. It is a square plus d by 2 minus L whole square to the power half, and expand it, neglect the higher order terms, you get a plus 1 by 2a d by 2 minus L whole square. So S prime S2 minus S prime S1 is equal to LD by A. For fringes to disappear, this LD by A must be equal to lambda by 2. This is the least condition for the fringes to disappear. Now that means L will be equal to A lambda by 2D. For extended source having width A lambda by D, for each point there is a point. Now we have, earlier we are talking about 2 point sources S and S prime. Now we are talking about extended source. Here is the diagram for extended source. See, S is the extended source having width L. Okay, it is at a distance A from the two slits S1 and S2. So for extended source having width A lambda by D, for each point there is a point A lambda by 2D away, which produces fringes that are shifted by half our fringe width. causing disappearance of interference fringe. Okay, you take the extended source, divide it into two. Now when you take the first point on the left and the second point that will cause disappearance of the fringe will be the first point of the second half of the extended source. Hence the extended hence for extended coherent incoherent source, that means we are talking about real sources. Hence for extended incoherent source of width L, when L is very less than A lambda by D for an interference pattern of good contrast. So what do we see? We see that for an extended source, okay, if the extension of the source is very less than A lambda by D, why A lambda by D is important? Because here you see A lambda by T is this value here. Okay, so when it's very less than A lambda by 2, no problem, we'll get nice interference pattern. But as it becomes now, okay, now for theta is equal to, from this adjacent figure we see theta is equal to of the order of L by A, almost equal to. So the condition for good true contrast is D is very less than lambda theta. Why? We have just replaced this by theta. Actually, if L is very less than A lambda by D, D is very less than A lambda by L. Okay, and A by L is replaced by 1 by theta. That is why D is very less than lambda by theta. This is the condition we need to maintain to get a good contrast interference pattern. Once again, for poor contrast interference pattern, now if when will be the contrast lost? When this D is approaching the value lambda by theta, at least. For diffraction theory, we know that it is not lambda by theta which has to be approached. When we do Fraunhofer diffraction, we will see that it is 1.22 lambda by theta, that is the value. D, if it is comparable to 1.22 lambda by theta, at least the interference pattern will lose all its contrast and can be considered to have vanished. Now that is not the only value, as I've been telling you, it's the least value. It can also vanish for 2.25 lambda by theta, 3.24 lambda by theta. Actually, poor contrast repeats itself at such values. After the least value of 1.22 lambda theta, it goes on, so on. The distance LW is equal to lambda by theta is called the lateral coherence width. Now see, this is something. Now why do we have to maintain a fixed value of D? Because of spatial coherence, because of extended source. Extended source means loss of spatial coherence. Now with spatial coherence, we have this concept of lateral coherence width. That means the width that has to be maintained between the two secondary sources in order to get good contrast interference pattern. So LW is equal to lambda by theta. The lateral coherence width is then actually the distance over which the beam may be assumed to be spatially coherent. Of course, when we are using an extended source, what is lost? It's spatial coherence that is lost. So D, when it is less than LW, if a good contrast is expected. So let's repeat. So L is equal to lambda by theta. LW is equal to lambda by theta, that is the lateral coherence width is then actually the distance over which the beam may be assumed to be spatially coherent, and D is less, when D is less than L omega, LW, then only we are going to get interference pattern of good contrast if we are using an extended source. An application of the lateral coherence width. What is the application of the lateral coherence width? Let's see. Let's take an example. Now, angle the sun subtends with Earth is 32 minutes. Okay, that is the equivalent of theta. Sunlight is filtered. Let's say we are doing an experiment. We have filtered sunlight so that we are only getting 5,000 angstrom as the wavelength. Now, this is made incident on a double slit arrangement. Now, as I told you, Sun is not a point source. Even though the distance of Sun is quite large from Earth, still it is an extended source and it subtends an angle of 32 minutes. What should be the distance between S1 and S2? That means what should be the value of D to get an interference pattern of good contrast? As I have told you, that in order to compensate the folly of an extended source, that is the value of L, we can change D. Okay, we have certain restrictions that we have to maintain to get a good contrast interference pattern. So what should be the distance between S1 and S2 to get an interference pattern of good contrast? I'm just using this value. Theta is equal to lambda by LW. Theta is equal to what? It is 32 minutes. Convert that into radians. That is 0.01 radian. Now LW is what? Lambda by theta. Lambda is 5 into 10 to the power minus 5. Why? Because it's 5000 angstroms. Divide that by 10 to the power minus 2. You will get 0.005 centimeters. So this is the lateral coherence width if I am using the sun as the source and if I am filtering out 5000 angstrom light wave from it. S1, S2 then must have a value less than 0.05 centimeters. That means D must be maintained a value less than 0.05 centimeters for good contrast interference pattern. Okay, so that is it. That is the end of my lecture. The lecture on coherence. And as usual, thank you. And if you need, I hope you're going to need certain clarifications and you need to clear your doubts. So I will be expecting your emails at my email address, or you can call me at my number. All of you know my number. Strangely, till now, except one, none of the students have called me up. I hope my lectures are going very nice. That's why everybody is being able to understand everything. If not, please do not hesitate to approach me. Thank you.